Hello, today we begin our review of polynomial functions. This is Unit 1B, and today we're going to kind of do a quick review of quadratics and then a quick review of polynomial functions of higher degree. So as with anything we do, as you're working through a problem, if you have questions, don't forget to jot that down so you'll remember to ask me when you come to class. And then if you go into the Unit 1 resource page and scroll down to Unit 1B, you will find this document that has all the information as far as like definitions and some models you might want to remember from Algebra 2, and it goes through all 5 sections in this unit. So it's kind of a help sheet, one-stop shop for things that you should know from Algebra 2, because again, this unit is another review unit. These are all things that you should have learned in Algebra 2. So in the notes that we're going to do today, we'll cover 2-1. So we're going to do a couple of problems there to refresh your memory, and 2-2. So before I get into the notes themselves, I'm going to kind of review you over some basic things with quadratics. So remember that the quadratic parent function is y equals x squared. And so you have this graph that's going to have an origin point here, go over 1, 2, up 1, 2, 3, 4, 1, 2. And then you go over 1, up 1, over 2, up 4, reflect that over the axis of symmetry, and you have your quadratic function graph, parent function graph that you studied that looks like that. That's 1 and 2, and that's 1 and 2. So that's that basic graph. Okay? So we talked about last year we had a general form or standard form. We had a vertex form. We know that when a, this number in front, is greater than 0, it's going to open up, and when it's less than 0, it's going to open down. We know that the vertex form is HK, and then we know if we need the vertex when we're in standard form, then we can use the negative b over 2a that we learned about last year, and then you take the negative b over 2a and you plug it back into the function, and that will give you your y value. We also know that the axis of symmetry is the vertical line that splits the parabola in half, and it's going to go through the x coordinate of the vertex, and it has to be written as an equation because it is a line. We found y-intercepts by substituting 0 in for x. We found x-intercepts by setting the quadratic to 0, and then you could either solve by factoring, solve by quadratic formula, solve by completing the square. Remember that completing the square when a is 1 and b is even is a really short way to come up with a solution. We also learned that we could solve for a, meaning that if we had a model and we didn't know exactly what that width of that quadratic was, which is one of the things a tells us, then we could plug in a value for the vertex, we could plug in another point on the graph, we could solve for a, and then we would be able to actually come up with the width. So we did that last year in Algebra 2 in a couple of different functions that we studied. So now as we look at some of the review notes, we're going to take this first set and we're going to compare everything to the quadratic parent function. So we're going to look at this and we're going to see what transformations have been applied to get this. So the first one, we have a vertical compression by 1/2. And we also know that because this is happening to the vertical component, that this is a value that would calculate and affect the y value. B is a vertical translation of 3. And so that means the width would be the same as the parent function, but it's going to move 3 units up the graph, so it's not going to be touching the origin at this point. Then we looked at the next one, which was x plus 3 squared. And because that x is inside the power of 2, then we know it's a horizontal affecting the graph, and it would be horizontal translation left 3. And then we have D, which has a few translations or transformations going on. We've got a reflection, we've got a vertical stretch, we've got a horizontal translation to the left one, and we've got a vertical translation down one. So there are several things there. Do remember when you're doing transformation, order is important because this has to reflect what's happening algebraically. And when we solve an equation algebraically, we do it in a certain order. We have an order that we undo the equation with. Well, if we don't have a specific order when we're doing our transformations, then we have an answer graphically that might not match an answer algebraically. So we want those things to match up. So Remember, your order is reflection, then stretch compression, and then translations. So it doesn't matter which one reflects as long as you do all reflections first, then all stretch and compression, and then all translations. And that way we'll ensure that our graph in a transformation will match up with our graph algebraically. Problem 2, we have an equation in standard form, and we are going to sketch it without using a calculator, identify the vertex, the axis of symmetry, and the x-intercepts. So the first thing I would do here would be to get rid of that 1/4, because we learned we are factoring. It's better to factor when a is a positive whole number. So I'm going to come over here and I'm going to multiply everything through. Actually, I don't need to do that on this one. My mistake. We are just looking for the vertex. So right now I'm going to use x equals negative b over 2a. So I'm going to calculate that because we have our b here, which is negative 2, and we have our a, which is 1/4. So when I calculate that, I get positive 4. And then I plug it back in the equation. Wherever there's an x becomes a 4, and I get negative 16. Notice the use of the notation. You would not just write negative 16 on your paper. That would be what I consider math magic. You need to tell me what that is. And so then the vertex should be a coordinate point because it's a location on the graph. To find the axis of symmetry, remember we said it was a vertical line that went through the x coordinate of the vertex. The x coordinate of the vertex is 4, so the axis of symmetry is x equals 4. Next, we're going to find the x-intercepts. And to find the x-intercepts, we're going to set the equation to 0. I multiplied the equation through by 4 to get rid of the fraction right here. So by doing so, then I could actually factor it. And so this is the factorization that I get. So x equals 12 and x equals negative 4. However, this would not be what you tell me because x-intercepts are a location on a graph, so we need a coordinate point. So to write this as a coordinate point, we put the x value here and the 0 and the x value there and the 0. And the last thing that we're going to do right here is calculate the y-intercepts. And that's the really easy one to do because to calculate the y-intercept, all you have to do is plug in a 0 for x. Because remember, a y-intercept is on the vertical axis, which has an x-coordinate of 0. Because we don't want to move left or right off the vertical axis. So when I put my 0 in here, I got negative 12. Again, writing it as a coordinate, so I get 0, negative 12. So notice you see the coordinate point here. You see coordinate points here because this is how you should have left that one. You see a coordinate point here. So you do have to pay careful attention to when you need to leave your answer as a coordinate point and when you can leave it as y equals. You can leave zeros, roots, solutions as x equals, but we want coordinate points elsewhere. So this is what this actually would look like. I plotted my x-intercept, I plotted my y-intercept, I plotted my axis of symmetry and my vertex, and I get this graph here that has a horizontal scale of 2. On question 3 in my notes, we're writing a parabola in standard form, and we're given a vertex point and we're given a point on the line. And then we also want to find the x-intercept, y-intercept, and the axis of symmetry. So this is one of those problems where you have to solve for y. So what I did was use the vertex form, and I plugged in the vertex here and here. Then I plugged in the values for x and y of that point that's on the line. So the y values here and the x values here. So now if you notice in this line right here, everything has a value except a. So I only have one unknown, and we can solve for that one unknown by moving the 2 over, and I get a equals 2, and that gets put right back into my equation right here. So I have the actual width of the parabola because I have an a value. I know which way it's going to open, up or down, because I have an a value, and then I have the vertex. So then the next thing I would do is find the x-intercepts. Well, to do that, I just wrote out my equation. I foiled it right here, remembering not to put x squared plus 4. I combined my like terms, and I got down to this in standard form, which is one of the things it asked us to do in the equation. So once I got it in standard form, I noticed that all of these were positive in even numbers, so I pulled out a 2, and that left me with something that's super easy to factor. And that means I have a root right here at x equals negative 3, which I would write as negative 3, 0, and one at x equals negative 1, which I would write at negative 1, 0. Then again, to do y-intercept, we plug in a 0 for x, so I plug in my 0 right there. It works out nicely as y equals 6, and it's a coordinate point, so I would write it as 0, 6. And finally, axis of symmetry. would be the line that goes through the x value of the vertex. So I would say x equals -2. So that takes care of our polynomial review of quadratics, which is x squared, so powers of 2. And now we're going to move into second degree or higher than second degree or higher order polynomials. So we're going to review a few things here and then we'll go through the examples. So the first thing I want to review is the definition. A polynomial has smooth, continuous, and changes sign only at 0. So it's a smooth, continuous curve and it changes signs only at 0. So for instance, a square root graph wouldn't be a polynomial graph because it kind of ends at that beginning point. A rational function wouldn't be a polynomial graph because it has all kinds of things that cause it to be not continuous, like holes and vertical asymptotes. A cubic graph would be okay because x cubed is the little wiggle graph. It's definitely smooth. It definitely doesn't have any breaks in it. But a absolute value wouldn't be a polynomial function because it has that sharp point at the v. So please make sure you remember the definition and wouldn't be surprised to see a question about the definition itself on the test. Here is the formal definition of a polynomial function. So you have p of x equals a sub n, x to the n plus a sub n minus 1, x to the n minus 1 plus a whole bunch of stuff plus a sub 1 of the x plus a sub 0. So basically what all this means is you notice this is a sub n, but now it's subtracting 1. That makes this smaller than this. And then the power, here's my power, but now I'm going to subtract 1, so it's smaller. So really this is the way that we would write setting up standard form. We always tell you to do the highest power of x first and then decrease your way down to the number, and that's what our a sub 0 is. I won't ever ask you to give me this formal definition, but I do need you to understand what it means so that you can write your answers in the correct form. So the first thing we're going to recap is in behavior. You learned in Algebra 2 things like as x approaches negative infinity, f of x approaches positive infinity means a graph falls to the left. As x approaches infinity and f of x approaches infinity, that means the graph rises to the right. So you do have to kind of think about that, what's going on with the graph when you look at that in behavior. The leading coefficient and highest power determine the end behavior. So as we're looking through this, I want you to kind of think quadratic and cubic. That's a good way. If you know what those graphs look like, then this becomes easy to navigate through. So if the highest power is even, so I'm talking about like x to the 4th, x to the 6th, x to the 8th, x to the 10th, and the a value is greater than 0, meaning positive, then it's going to behave like the quadratic on each end. In other words, both ends are going to go up. If it's even and it's less than 0, that means a is negative, and so the ends are going to do the same thing, but they're going to turn upside down. So it doesn't matter how many times it wiggles or moves inside here, the ends are going to do the same thing. If it's an odd power, think a cubic function. And so if it's a cubic function and a is positive, that's like the cubic parent function, so you would have down, up. But if a is negative and this graph turns upside down, now you have up, down. And so that's one of the ways you can kind of determine the end behavior by looking at the highest power and then the leading coefficient. This is all listed out on that help sheet. It doesn't have the pictures, but it's the same idea. All right, then we have multiplicity, or repeating or multiple roots, and we determine that by the exponent of the factor. And so, for instance, if I have x plus 3 squared, the power is 2. That's what the little power up here is. And then the factor is a multiplicity of 2. So we would actually write m2 of 2, and it's at x equals -3. So it's occurring at -3, and you have 2 of the same root at that point. If it's odd, then it's happening at this place. So we have x at -4. But this is odd and it's a 3, so it would be multiplicity of 3. So then you might write m3, and then it means you have 3 of the same root at the same point. And finally, the other thing we learned about root behavior when you have repeated zeros is that there's a certain behavior that exists at that 0. So by knowing this is a multiplicity of 2, we know that it's going to touch and turn or bounce for even exponents. So For instance, if I have, it's upside down, but I have a power 2, it comes up here, it touches the x-axis and goes back. It could be up here, touch the x-axis and go back. But that's what we say a bounce is, and so that's what happens when there is a multiplicity of 2 at a specific root. When there's a multiplicity of 1 at a specific root, it's going to just cross straight through like a line, which, all lines have x to the power of 1, so that kind of makes sense. So this is an odd multiplicity of 1, so you would say m1. Here we have an odd power, but it's greater than 1. So when that happens, 3, 5, 7, 9, we get this little wiggle action going on right there. The bigger the power, kind of the flatter it appears in there, because that means through that part of the graph, it's changing in really, really small increments. So we say it wiggles if it's 3 or more odd. We say it crosses if it's an M1, and we say that it bounces or touches if it is an M2. Okay? So I'm going to write that on here because I noticed that's not on. So multiplicity of 2, M2, multiplicity of 1, M1, and multiplicity greater than 1. So let's say example M3, just so you have those in your notes. All right, so now we're going to kind of go through a problem. We are going to find the 0 and sketch. So here is the problem that I have. The problem is f of x equals negative 2x to the 4th plus 2x squared. So I need to know the roots, and so to find the roots, I'm going to factor this out, bring out a negative 2x squared. I'm left with x squared minus 1, which factors out to x plus 1, x minus 1. So the roots are 0 here, negative 1 here, and 1 here. So this power right here is 2, so that means I have a multiplicity of 2. The power on this one is 1, so I have a multiplicity of 1. The power on this one is 1, so I have a multiplicity of 1. So remember, the multiplicity tells us about the root behavior. So when it's a power of 2, it's going to bounce. When it's a power of 1, it's going to cross straight through. Okay, so as I'm deciding how this is going to work out, I want to start with my roots. So I would put my roots on here of negative 1, 0, 1. And then I would look at what my end behavior is doing. So it's a power of 4, so I know the ends are doing the same thing. A is negative, so it's less than 0, so that means both ends point down. So you can see I went to my root and I put a down arrow and a down arrow. And then I look at what's happening, so I know that this is going to, at negative 1, it's going to cross. So at negative 1, here's where my end started, and then I came straight up here, and then I've got to hit 0, which has a multiplicity of 2, so I need to bend around here, bounce at 0, and go back the way I came. And then at 1, I need to cross straight through, so I turn and connect it with this end right there. So that's kind of the process that you go through. So on question B, it's f of x equals 3x to the 4th minus 4x cubed. So again, I factor, and that means I have a root at x equals 0 and a root at x equals 4 over 3. Notice the notation. It's not just a 0 and a 4 over 3. You need to identify what it is you're doing. So the power on 0 is 3, so that's a multiplicity of 3. The power on this binomial is 1, so that's a multiplicity of 1. So power of 3 means it's going to wiggle, and power of 1 means it's going to cross. The highest power here is 4, and A is even, or positive, excuse me. So that means both ends are going to point up, just like the quadratic. Okay? So then I have my two roots right here. And it should wiggle right here, and it looked more like a wiggle before I kind of thickened up my line here to make sure I went through my points. So, kind of be careful with that. So it should wiggle right here. So I did up, up. So at this point I went out, at this point I went out. And I know that it's going to wiggle here. So I should have kind of had a little more, well, I did, but not anymore. It looks like it. And then it should cross straight through, so I'm coming down here and connecting it back here with a straight through cross. You could use a plus minus number line if you wanted to verify your graph. I would use my roots of 0 and 4/3. I'd pick a number over here and I got positive, and I picked a number in the middle and got negative, and I picked a number over here and got positive. So look at the graph. Over here, it's positive. Between the two, just like on the plus minus number line, it's negative. And then over here on this side, it's positive just like it is right there. So you can definitely use that plus minus number line to help. And as far as how high or how low the hills or valleys are in this graph, I'm not super picky about that because we are doing a little bit of estimation, and we'll pick up more how to find those points of inflection next year in calculus. All right. So here is C. So we are going to use this in standard form. So what I did here is I needed to get that fraction out of there, so I divided out a 1/2, a negative, and an x. So this is the same thing as negative 1/2 x. And I'm left with this trinomial, which is a perfect square trinomial, so it factors down to here. So here's this factor, which equals 0, and this factor, which equals x divided by 2, or 1/2. So you're just pulling this piece out right here, and that's what we're working with. So the power here was 1, so it's a multiplicity of 1, and it's going to cross. The power here was 2, so that's a multiplicity of 2, and it's going to bounce return. And remember, we learned in Algebra 2 that this degree right here tells you at most how many solutions you could have. So we know we could at most have 3, and there's 1 here, and there's 2 right here. So 1, 2, 3, because that's a double one right there. All right, so then I looked at the power, which is odd, and a is negative, so it's going to behave like the cubic function, and it's negative, so it's turned upside down, so we have up, down on the end behavior. So I went to my root, and I went up, and I went down, and then I looked at what was going. So at 0, it's going to cross straight through. At 3/2, it's going to bounce up and come back out the way that it started, and here's a number line to show that my graph does match. So this is positive from 0 that way, it's negative from here to 3/2, and then it's negative again from there. All right, in problem 2 in this section, we're going to find zeros, multiplicity of zeros, and sketch the graph. Again, all without a calculator. So at this point, I have this particular function, and I pulled out the GCF, which was 3x, and I'm left with this part. Unfortunately, this part is not factorable. So when it's not factorable, you don't tell me there's no solution. You either use completing the square, which I worked out right here in case you needed to see it, or the quadratic formula, which I worked out right here. So when I get 2 plus root 3, that's about 3.7. When I get 2 minus root 3, that's about 0.3. So I want to know that to be able to know what's going on. So I'm going to come up here. This is 0 has a multiplicity of 1. We know this is quadratic, so we're talking about 2 things there. We know that the power is odd, so that's 3. We know that a is positive, so that means it's cubic in the sense that the ends are going to go down up. Okay, so then I put my roots roughly in here, kind of sketched them in from my estimations, and then I went down up because that's what the end behavior is doing, and then I looked at the root, so it's going to cross, cross, cross. And so that's how I would get my graph. And remember, it's not important how low or how tall these valleys are, as long as it's fitting the general pattern. The next problem we're going to look at is a polynomial of degree 3 with zeros at -2, 4, and 7. So this is kind of a problem we'll talk about a couple of different things. So first, we're going to start with the zeros. So the zeros would be these 3 ones that they give us, and so that's x equals -2, x equals 4, and x equals 7. So then, now that we have our factors listed out, we can step it backwards, or excuse me, our zeros listed out, we can step it back to a factor. So if it was x equals -2, the factor would have been x plus 2. If it was x equals 4, the factor is x minus 4, and if it was x equals 7, the factor is x minus 7. So notice it said it was a degree of 3. That means each of these binomials have a power of 1. Because we know when our polynomial is factored like this, to get the degree, we add up the powers of the factors. If it's in standard form, we can just look at the highest degree. So since I have 3 roots and I want a degree of 3, then I'm going to keep it simple and make a1, and that's going to be my factored form polynomial. If I want to put it together to make a standard form, then I would take 2 of them and multiply them together, which got me x squared minus 2x minus 8. Then I would multiply that by x minus 7, and then I get this lovely polynomial. So I have to be really careful in my math here. This is only one example. I could have done the same thing and put an a value of 2. I could have put an a value of -1. I mean, I could have made anything I wanted and made a different equation. However, we're going to keep it simple, and if at all possible, use 1 just to make the math a little bit easier. The fourth one here is a polynomial of degree 5, and it gives us 4 roots. So we can already see from the beginning there's a little bit of an issue here. A degree of 5 means I should have 5 roots, but I'm only given the 4 roots here, which means something else is going on. So I'm going to start it the same way. I'm going to say x equals -3, x equals 1, x equals 5, x equals 6. Then I'm going to list my factors, x plus 3, x minus 1, x minus 5, x minus 6. However, that if I add them up, 1 plus 1 plus 1 plus 1 is 4, not 5. So what I have to do to take care of this is to up the multiplicity of one of my factors. And just as a general rule of thumb, I always pick the easiest one to work with. So I'm going to come here to the x minus 1, and that's the one I'm going to make have a multiplicity of 2. So it's 2 plus 1 is 3, plus 1 is 4, plus 1 is 5. And so now I have a degree of 5. If it asked me to put it in standard form, then I would take this probably and multiply it out, and then take these two things and multiply it out, and then I'm going to have to multiply the x minus 6 in there, and you can see the math gets a little gross really fast. So let's hope we don't have to do that too often, and we can stop right here where it's factored. But in any case, if you do have to do this, you've got to be super careful. 1 minus in the wrong spot, your whole answer would be wrong. So just be careful on that. The last thing I want to talk about is what we call the intermediate value theorem. And this is a theorem that you learned in Algebra 1. You touched on it again in Algebra 2. You had geometry in between, so you had to kind of relearn it in Algebra 2. We're going to touch on it a little bit this year, but it is it's a theorem that we use a lot in calculus. The intermediate value theorem is a theorem designed to prove existence. And so it reads, if a and b are real numbers and a is less than b, so a has to be smaller than b, on the closed interval. So the closed interval means you've got an interval with hard brackets, meaning the 2 endpoints are included. Well, when I do f of a and get a function value, and I do f of b and get a function value, the function value of a has to be not equal to the function value of b. They've got to be different. And when that's true, then f takes on every value between f of a and f of b. So that means all the y values between f of a and f of b. So for example, if the interval was -3, 5, closed interval, and you don't have a function to work from, so they've probably given you these. F of -3 equals -15, f of 5 equals 4. So f of 3 is less than f of 5. It's not the same thing. Then the function will have every y value between -15 and 4, somewhere in the interval. So that's how that kind of works. Find an interval 1 unit in length in which the function is guaranteed to have a 0. Remember we said it was a theorem of to guarantee something or to prove something, not disprove it. So we're guaranteed to have a 0. So we're going to use the equation. So what I did is put this equation in my calculator, and I wrote down the table. So what I'm looking for is 1 unit interval that guarantees I have a 0. It guarantees I have a g of x equals 0. So that's going to occur when the y values change from positive to negative. When they're physically going from the top of the graph to the bottom, they have to pass that horizontal axis or vice versa. So when I look at my y's, I can see 13 and -4. I see that sign change that happened right there. So according to the intermediate value theorem then, because I have this change, it's going to occur somewhere between -2 and -1. And so the sign change is what we're looking for to tell us what's happening over here. So on this one, I see another sign change from -3 to 4. So the y values change from negative to positive, which means there is a 0 guaranteed between 0 and 1. So that's kind of how that intermediate value theorem works. It's guaranteeing by knowing that there's a sign change that there is going to be a solution or a root of 0 on the other side. All right, so that takes care of all of the examples that we talked about. Don't forget about the help sheet on the unit resources if you need it. And next class period, we will be moving on to polynomial division. Thanks so much, guys.